All right, let's dive into the fascinating and sometimes confusing world of deep learning. So, what is it really? Well, at its core, it's this incredible way for machines to learn from experience, building up a really deep, layered understanding of the world around them. We're going to break down exactly how it all works, one key idea at a time. Let's get into it. To get us started, I want to pose a really big question. It sounds simple, but it's actually profound. How does a machine learn to see? How can a bunch of code look at a picture and have any idea what's in it? This is the core challenge that's going to guide our entire journey today. Believe it or not, for many of the pioneers in this field, the answer started right here. This is the famous MNIST Dataset, just a massive collection of handwritten digits. It's a classic rite of passage for anyone getting into AI, and it is the perfect case study for us to really get how a machine goes from knowing absolutely nothing to recognizing the difference between a 3 and an 8. Okay, so if we're going to teach a machine to see, we first need to, well, build the machine, right? So let's start by assembling the basic components, the skeleton of what we call a neural network. This is our learning machine. The most basic design, the starting point for almost everything, is called a feedforward network. And honestly, the best way to picture it is like an assembly line. Information, in our case the pixels from one of those handwritten numbers, goes in one end, it gets processed through a series of stations, and then a final decision, a guess, pops out the other end. That's it. No loops, no going backward, just a straight forward flow. So what are those stations on our assembly line? We call them hidden layers, and you can think of them like a team of specialists. The very first layer might just be responsible for spotting simple things, like little edges and curves in the digit. The next layer takes that info and starts looking for bigger shapes, like loops and straight lines. And the layer after that puts those shapes together to recognize the whole number. Each layer builds on the last, creating a more and more complex understanding. Okay, but wait. How does any one of those tiny specialists decide if what it found is actually important enough to pass along? That is the job of the activation function. It's like a tiny little on-off switch inside each artificial neuron. If the signal is strong enough, the switch flips on and the message gets masked to the next layer. This simple switch is absolutely crucial. It's what allows the network to learn really complex, wiggly patterns, not just simple straight lines. It's how it learns the gentle curve of a handwritten 2 versus the sharp angles of a 7. All right, so we've got the basic parts assembled, we have our machine, but right now it's just an empty shell. It doesn't know anything. Now for the really fun part, we have to actually teach it. So let's look at the training loop, the process where our machine learns from its mistakes. You know, when you peel it all back, the core of deep learning is actually pretty simple. It's this cycle, this loop that just repeats over and over and over again. First, the network looks at a digit and makes a guess. I think that's a 7. Then we measure the error. How wrong was it? Third, we use that error to make teeny tiny adjustments to all the connections inside the network. And fourth, we just do it all again, thousands, sometimes millions of times. So that second step, measuring the error, how do you even do that? How do you put a number on wrong? Well, that's what the loss function is for. Think of it like a score. If the network sees an image of a 7, but it guesses a 1, the loss function spits out a really high number. The entire goal of training is just to get that loss number as close to 0 as humanly possible. And that leads us to the real engine of learning. It's a mouthful, I know, but it's called Stochastic Gradient Descent, or SGD for short. This is the algorithm that actually does the adjusting. After every single guess, SGD looks at that loss score and figures out exactly how to tweak every connection in the network to make a slightly better guess the next time around. It's like a ship's captain making thousands of tiny adjustments to the rudder to steer the ship exactly where it needs to go. Now, you wouldn't expect to master a subject by reading the textbook just one time, right? Same idea here. The network has to see the data again and again. And that's where the term epoch comes in. One epoch is just one complete pass through the entire training dataset. Models don't learn to recognize all those digits after seeing them once. No way. It takes many, many epochs, getting a little smarter with each complete review. Okay, so this whole process is really powerful. It is, but it's not always a smooth ride. There are these common pitfalls, kind of like the classic villains of the story, that every single person building these things has to learn how to fight. And maybe the biggest challenge of all is this balancing act. On one side, you have overfitting. This is like a student who just crams for a test. They memorize the exact answers to the practice questions, but they don't actually understand the material. So the model does great on the data it's already seen, but the second it sees a new digit, it fails completely. On the other side is underfitting. That's a student who didn't study at all. The model's just too simple, and it can't even find the basic patterns. And then there's this other, more internal problem. It has to do with that correction signal we talked about. In really deep networks, as that signal travels backwards through all the layers, it can get, well, distorted. Sometimes it can fade away into a whisper, that's a vanishing gradient, and when that happens, the network just stops learning. Or it can grow into a deafening scream, an exploding gradient, and that makes the whole network completely unstable. So, how do you fight these villains? How do you solve these problems? Well, just like the slide says, we need some clever tricks. And luckily, over the years, computer scientists have come up with some really ingenious ones. And one of my absolute favorites, just because it's so clever, is called Dropout. Here's the idea. While you're training, you randomly just turn off some of the neurons for each guess. It's like forcing a team to work together, but with the rule that on any given day, any member might be absent. What happens? Well, it forces the remaining neurons to become more robust, more independent, and it stops them from relying too heavily on any single other neuron. It's a brilliant way to fight overfitting. All right, so everything we've talked about so far is for a kind of general-purpose network. But what happens when you're dealing with very specific kinds of data? Like images or sentences? Well, that's when you need specialized brains for the job. And boom! Right here, this is the answer to that big question we started with. Convolutional neural networks, or CNNs, are the reason machines can see. They are literally inspired by the human visual cortex, and they are built specifically to find patterns in images. They use these special filters to find edges, then textures, then shapes, building up that same complex understanding we talked about earlier, but in a way that's perfectly suited for visual information. But images are one thing. What about something like language, where the order of the words means everything? For that, we've got something called recurrent neural networks, or RNNs. These networks have a kind of memory. They have an internal loop that lets information stick around, so they can actually remember what happened at the beginning of a sentence to help them understand what's happening at the end. They're built for sequences. Okay, this is getting pretty wild, right? Our machines can see, they can understand language, but can they create? This brings us to one of the most exciting frontiers in all of deep learning. Models that don't just analyze data, they create entirely new things from scratch. This leads us to one of the most brilliant ideas in all of AI, Generative Adversarial Networks, or GANs. And the concept is it's a duel. You have two networks fighting each other. The generator is the artist. Its only job is to create fake images, like new handwritten digits that look totally real. The discriminator is the critic. Its job is to tell the difference between the artist's fakes and the real thing. They're locked in this constant battle, and as they compete, they both get better and better, until the artist is creating fakes that are absolutely indistinguishable from reality. Now, you might be thinking, this all sounds incredibly complex. And you're right, it is. But people aren't building this stuff from scratch every single time. They rely on these amazing toolkits that make it all possible. You'll hear names like TensorFlow, PyTorch, and Keras thrown around a lot. Think of them as the workbenches for deep learning. They have all the pre-built parts, and they handle the really heavy math, so creators can focus on designing new architectures and new ideas. TensorFlow is a powerhouse for big production-level projects. PyTorch is loved by researchers for how flexible it is, and Keras is famous for being super fast and easy to get started with. These tools have truly opened up the field to so many more people. So let's just take a step back for a second. We started with this simple question: how does a machine see? And we've journeyed through building the machine, teaching it through trial and error, fighting off common problems, and even giving it a spark of what looks like creativity. We've taught it to learn and recognize patterns with incredible accuracy. But that leaves us with one final and much bigger question to think about. We've taught it to learn, but does it truly understand?